Okay, I've been asked about homework. Which page was it and what number? Uh-huh. 41 and 43. Let's do 43 because I think that actually that's what I wanted to start class with today, was something like that. Because I spent most of class last time doing inverse sine and cosine, but I didn't have a chance to do an inverse tangent. So number 43. You are given the inverse tangent of tangent of 4 pi over 5, right? Yes? Okay, so here's the deal. With last class, the very end, I summarized the properties for the inverse trig functions. And here's what they were, all right? So we spent a lot of time doing, well, we did cosine inverse, we did sine inverse, which is in a prior page, somewhere before this. Where is it? Here it is. But the important thing here is that when you're putting inverse tangent together with tangent of anything, doesn't matter what it is, it should spit out whatever's there. But there's condition that whatever was in here had to be between negative pi over 2 and pi over 2. That's what it had to, for this to work, that's what has to happen. So what we're going to do is, on this problem, we're going to notice that the angle we're given, 4 pi over 5 in here, the question is that between negative pi over 2 and pi over 2? Yes or no? No? How can you tell it's not in between there? How can you tell? You put in your calculator, yes. Here's another way to look at it. Do you agree that 4 pi over 5 is the same as 4 over 5 times pi? That's the same thing there? And then pi over 2 right here is the same as half of pi. Yes? So the question now is, here's 1/2, here's 4/5. Which fraction is bigger? 4/5. So this is actually, 4/5 is actually bigger than 1/2, which means that it's bigger than pi over 2, which means it's not inside this interval. That make sense? So it's not just going to spit out the answer of 4 pi over 5. So the way we can do this is try and figure out on the unit circle, where is 4 pi over 5? Where is it? We know it's bigger than pi over 2, right? But it's smaller than pi? Yes? So it would be something like, and it's not one of our common angles. That's kind of what's confusing about this. But we know that if we take pi, which is a half rotation, and we were to cut it into 5 equal pieces, it would be at the 4th one. That make sense? Or not? No? All the way is pi, isn't it? All the way is pi? Okay, from here to here, that's pi over 2. We know that 4/5 pi is bigger than pi over 2, so it's got to be somewhere in the second quadrant. Now I'm putting it close to pi. I'm putting it over here because 4/5 is really close to 1, right? So I'm just kind of guesstimating where it is. It's somewhere over there, yes? And tangent, by definition, the tangent This is an x and this is a y coordinate, correct? We don't know what it is because it's not a common angle. But the tangent should be the y divided by the x. Yes? Okay. Which one of those is positive? Which one of those is negative? The x and the y, are they both positive? What's the deal here? X is negative and y is positive, correct? So when I take this y and divide it by the x, that's what tangent would be, but I don't know what it is, right? So the restriction, in order for me to use this inverse trig function, I must only be looking, I have to cut this off, I can only look over here in the first quadrant and the fourth quadrant, because that's the restriction that I have on the inverse tangent, that I have to be between pi over 2 and negative pi over 2, right? So can you think of another point on the circle that's in either quadrant 1 or quadrant 2 that has not the exact same x and y, but it would give you the same ratio? In other words, can you think of something that's over here that the x value would be exactly the same, but maybe not negative, instead positive, and then the y value would be exactly the same, but instead of being positive, it would be negative? Yeah, or nay? Not in the first quadrant. Couldn't be in the first quadrant. How about directly across like this? Do you agree here that the x value, which the x is this distance, right? That goes, if we draw a right triangle, x is the distance, this yellow distance from here to here, and it's negative because I'm going to the left. Do you agree if I just mirror that to the other side, I get the same distance the other way, but now it's positive? You follow that? No, now the y is going to be negative, okay? And now the y value is the distance up and down, which is that little blue, but now it's the same but the other direction. So I have over here the same x and the same y as far as like what the number is, right? But it's switched in signs. This time, this x is positive and the y is negative. Does that make sense? Now, if I say tangent of this, won't I get the exact same answer as if I do tangent of this? Yes, because this one, the x and y's are exactly the same. This is positive, this is negative, this one's negative, this is positive, so you'll get the same answer. It'll be negative, right? So what you need to be doing is asking yourself what this angle is right here. What's this angle that goes from here backwards? Backwards means it's a negative angle, right? Okay, so I'll try and help you with this. From here to here was how much? 4 pi over 5, or 4/5 pi, right? That's what that was. How much more would I need to rotate to get to pi? 1/5, right? This is 4/5 of the way. 1/5 more and I'd be there. Do you agree? So that little measurement right here of 1/5 pi is the same as this measurement right here, 1/5 pi. Do you see that by the kind of the symmetry of the circle? So I can deduce from this that this angle right here has to be negative pi over 5. And it's negative why? Because it's a clockwise rotation. So tangent of 4 pi over 5 is exactly the same as tangent of negative pi over 5. And negative pi over 5 is inside this interval, which means that when I do inverse tangent, it should spit out what? Negative pi over 5. I'm glad you asked this question because that is, like I said, the first thing I wanted to start class with today. We had not done one of those in class. And you can see these are a bit more involved, right? Especially if they give you an angle that is not as common. You know, if it's pi over, you know, if that was 2 pi over 3, then that would be a little bit easier to do. Okay, do you still want me to look at 41? I'm sorry? No? It's very similar, right? Because the angle they give you, 9 pi over 8, would be outside of your domain, and then you have to draw it. Look, I don't mind doing it. I really don't mind doing it. This is a good exercise. We are kind of strapped for time today, but Okay, the property that we have for arcsine is that if you take sine inverse of sine of x, this should spit out x, but only if the x is where? What's the restriction on the arcsine? Negative pi over 2 and pi over 2. So it's the same restriction for arcsine as it is for tangent, right? Arctangent. What is the restriction for cosine? 0 to pi, right? That's different. Yeah, it's same bounds, but not the closed interval. Yeah, good point. Okay, so now I look at this angle and I ask myself, is that within that interval or not? Well, again, you can look at 9 divided by 8. That's bigger than 1, isn't it? So that's actually bigger than pi, which is way past pi over 2. So I'm going to go to a circle. 9 pi over 8. You can imagine like cutting this thing up like 1, 2, 3, 4, into 8 little sections, right? Sorry. And you're going to the 9th one, right? I don't know if I drew enough lines there, but you get the idea. You're counting by pi over 8, pi over 8, 2 pi over 8, 3 pi over 8, 4 pi, all the way you get 8 pi over 8 is pi. 9 pi over 8 would be a little bit past pi. With me? Okay, nay? Okay, so this point right here has an x-coordinate and a y-coordinate, doesn't it? I don't know what they are because it's not a common angle. But tell me about the x value and the y value. Which one is positive, which one is negative? Or, in this case, they're both negative, right? But all I'm focusing my attention on is which one of these? The y. Why? Why am I? Because we're talking about sine, right? And on the unit circle, sine is the y-coordinate, sine of the angle. So I want to focus my attention on this. I realize that, again, because I'm dealing with arcsine, I am not allowed to be in these quadrants. So I need to figure out another point on the unit circle that gives me the exact same y-coordinate as this. So where is it? Quadrant. So look, let me draw it in quadrant 1, and you tell me why it's not the point straight across here. Why is it not that point? Because the y is positive there. You don't want that, do you? See, with tangent, we wanted to go straight across because it switched both the signs, didn't it? In the last problem, we wanted the positive to become negative and negative to become positive so that when we did the ratio, it stayed negative. Here, we do not want the y-coordinate to change. We want it to be exactly the same value. We want it to be negative also, right? So that's not going to fly. So instead, it's this point here. So that has some x-coordinate and some y-coordinate. The x-coordinate here is positive, right? And the y is negative. But all I'm concerned with is that this y matches, right? Those two match exactly. So tell me about that angle. It's the same as this angle right here, isn't it? I'm pointing to this angle right there. It's the same as that little piece, but it's this way. It's a clockwise rotation, so it's negative. So what's that little distance right here as an angle? What is it? But as in radians, what is it? It's pi over 8, right? Because how did you get there? Pi over 8, 2 pi over 8, 3 pi over 8, all the way straight across was what? 8 pi over 8, and then 9 pi over 8. So it's just one of those pi over 8s, yes? So that's what it is the other way, yes? How did I know? Because what is 8 pi divided by 8? Right? Because the 8 over 8 would give you the 1. It goes back to how we did when we were, taking our common angles, and we start out with pi over 6 was our first one. Then we could count out how many? 2 pi over 6, which was the same as pi over 3. And then we did 3 pi over 6 was straight up and down. But 3 pi over 6 is 1/2 pi, or pi over 2. And we counted our way around. I'm doing the same thing. 9 pi over 8 means I'm going to cut pi into 8 sections and start counting around. And when I get to 8 pi over 8, I'm at pi, and then go one more eighth of a pi rotation. Yeah? Okay. So if this is pi over 8, just that little distance, then it's same on the other side, but because it's clockwise, I go down, so it's a negative angle. So it should spit out what? Negative pi over 8. Yeah? Yes. Uh-huh. Negative pi over 2 to pi over 2. Always. Yes. So if you want to do just a visual summary, when you're dealing with arc sine, you're always going to be cutting off the left side here. If you're dealing with arc cosine, you're always going to be cutting off what? The bottom two. And if you're dealing with arc tangent, you're also going to be cutting off the left two. And then, of course, there is also that restriction that with arctan, you can't actually be at negative pi over 2 and pi over 2, but let's not get into that. Okay? All right, well, we have a lot to do. You handed in quizzes, and I was really trying to get those quizzes graded so that you could get them back, so that you could have something to look at, to study, look at your own graphs, see what mistakes you made. And as I started grading them, I realized, man, there's just so much detail in there that needs to be checked. I knew last night there was just no way I was going to be able to get that done in time. So what I did, if you go to our Canvas page, and I sent an email, I sent 2 emails to you yesterday. I sent one that has the review for the test, which is a bunch of problems out of the book. They're just out of the chapter reviews. Those are the problems I suggest you go over along with your homework assignments, along with the problems we've done in class. Use that as your review for the test. Here it goes. But then after I sent you that email, I decided I would send you the I think they're very detailed solutions to the quiz that I was trying to grade for you. All right? So I'm going to hand those quizzes back to you. They are graded, meaning I've given you a numerical grade. I looked at it. Did you attempt all the problems? Did you try the bonus where you did the cosecant and cotangent, and then gave you a grade based on that? If you were missing 2 problems, then I took off, or whatever. But it has not been graded the way it would be graded for a test. Like, I have not checked your x-axis to make sure you labeled all your tick marks correctly. I did not do that. So what I'd like you to do is go in, and I don't know, this does not want to open. You go in, open up our Canvas page. I'm going to try and get this network hooked up here. There it goes. So if you go to our Canvas page, you go to Files. I actually included it in the email, but if you go to our course Files, I have a new folder in here called Solutions. Right there, Solutions. You click on that. It says Quiz Solutions on Trig Graphs. So if you download this, it shows basically what I would be looking for on a quiz, or on your test, when I ask you to graph something. So the first 2 was the first quiz that you did. It was on the 25th of October, I think is when it was due. It was graphing 2 trig functions, sine and cosine. So just notice some of the things I included. I included my work setting the argument of the trig function equal to 0. I included very detailed labeling of each of the points. I noticed on some of your quizzes, you labeled where it hits the x-axis, but you didn't label where these peaks were. You have to have labels for those. Now, on your test, I'm going to ask for 1 period and 1 period only on everything. All right, I'm not going to ask for 2 periods, but on this quiz, I did. Also, I show my work of where I plugged the values into the function to figure out where things were. Yes? Understand? So what I'd like for you to do is take your quiz and say, how close am I to that? What am I missing? And just think about, well, how many points would be taken off? If you have a graph, but nothing is labeled, you're going to lose a lot of points. And then the other problems, there were what, 6 of them, I think? These were pretty detailed. You know, I'm labeling all my marks again. You should always have at least 5 points labeled. You have your amplitude labeled. In this case, I'm labeling my vertical asymptotes. This one, same thing. Notice again, I'm setting my argument equal to 0 and 2 pi, and I'm showing that work. I'm also showing the work here of how I found the middle point between these 2 points by taking their average, which for this problem wasn't that big of a deal. It's, where was it? This problem, I think this is the one someone asked about in class, to begin class last time. But look at, I mean, this one, I showed each of the steps where I went and found the middle between each of those points. I'm showing that work. All right? I don't know. Yeah. I'll make the test, but it'll be based on, you know, the things we've done in class. And, you know, I looked back, I think your first test did not include things with like linear speed. Did y'all talk about like linear speed and arc length? Y'all did not talk about linear speed and arc length? Okay. I'm not testing you on that because I'm only testing you on things that we have done together. That's all I'm testing you on, all right? So if it was anything before I met you, I'm not putting on this test, all right? I think that's fair. Okay, so again, go through this, see what details you're missing, and then if you need help, come talk to me, text me, email me, all right? No, I plan on, I mean, I'm treating this like, you know, day one for us was day one for us, and that's all I'm going to test you on. Okay, let's get going. We have a lot to do. The problems, if you check, please check your inbox in Canvas. I'm just going to pull up. Come on, this thing is so darn slow. Forget it. Forget it. Okay. I don't have the patience to wait. All right, so we're going to get into 8.3 today. All right. This section is one of the most useful sections for you going forward and doing more math. Okay, as a student coming into Calculus 1 class, one of the things I always ask, you know, do you know your unit circle is always the first thing. And then the next thing is, can you solve trigonometric equations? So this is our first introduction into trig equations. 8.3, solving trig equations. Now, I'll just remind you that anytime we solve an equation, we have different methods for doing them. Like if I said 2x plus 1 equals 0, I said solve for x, you would approach this by moving the 1 to the right side and then dividing by 2, right? But if I gave you something like this, x squared equals x plus 6, now this is a quadratic equation. And normally what we do to solve a quadratic equation is we move everything to one side, get a 0 on one side, and then we try factoring, or we try like quadratic formula. Some of you got beat to death with the completing the square, right? But the idea is that the technique for those two are completely different, right? Yes, you agree with that? Okay. And then you have something like this, square root x equals x plus 2. Now you have a radical equation, right? You have a square root in here. The technique for solving that is different than the two before it. Here you would have to square both sides of the equation, and then when you did that, you would turn out having a quadratic equation, and then you would try and solve that. But again, different sort of approach than the previous two. And then you have things like this: x over x minus 1 equals 4 over x plus 2. This is called a rational equation. So we have a technique for doing this. We say, all right, we find the LCD. We multiply both sides by the least common denominator. I'm not expecting for you to remember all of this right here, right now, except to remember that there are different ways you attack different equations, right? Now what we're going to introduce are equations that involve the trigonometric functions and how we go about solving those, all right? And it's going to be a new method. It's going to require good knowledge of our unit circle, and I think you'll hopefully start catching on. So we're going to start with our first example, 8.1.4, or 8.1.2. 8.1, Jesus. Telling you, I remember I said it's too early for me. Okay, 8.3.2 is our first trig equation. I'm going to make it as basic as it can possibly get here. All right? Solve sine x equals 1. Now remember, the thing that goes into the trig function, right? The thing that you plug into a trig function, we call its argument. Yeah? We call it the argument. Is usually a what? A number or an angle? An angle, right? So what I'm saying here is, what angle do you plug into the sine function in order to get a value of 1? So what is it? What's that? Pi over 2. So here's the way that I would maybe approach this. I would say, all right, on my unit circle, the sine function is the y-coordinate, right? I'm looking to see what angle I turn to give me a y-coordinate of 1. And the only place that that happens is straight up, right? Yes? We've done this before. This is not brand new, all right? So what we're going to have is an angle here, an x value of pi over 2. So does everyone agree that that is a solution? Yes? Sine of pi over 2 should be 1. But is it the only solution? No. This is where we start to run into some issues. Because we talked about this probably about 2 weeks ago, this idea of a general solution. That I can actually be at pi over 2, but I could also get back to pi over 2 by adding a full rotation, right? Or I could go the other way, a full rotation, get back to the same place. So I should actually say, instead of pi over 2, I should say pi over 2 what? Plus, how do I say add any number of full rotations? 2 pi k, right? Did we use k or n? K? All right. So we say 2 pi k. And we said a couple of weeks ago that when we say k, we're saying k is an integer. K can be 0, 1, 2, 3, forever, or -1, -2, -3. So that gives you your pi over 2, and then that gives you a full rotation, either direction, as many as you want, and you'll always be pointed straight up. And so that gives you all the infinite number of answers, yes? Okay, this is the answer. Okay, that is the answer. Your answer is actually a general solution. We call that the general solution right there. Now, let me change the problem slightly. Solve sine x equals 1. I want to use the same notation the book uses, where 0 is less than or equal to x is less than 2 pi. So now what the problem is saying is solve this equation However, instead of giving me the infinite number of answers, right, give me only the answers that are between 0 and 2 pi. Yeah? That's the only place you're allowed to look. So just pay attention to the way I'm going to do this, because you may be thinking to yourself, oh, well, the only answer between 0 and 2 pi is pi over 2, right? That might be what you're thinking. And that's correct, but it'll get you in big trouble later if you just try and visualize it that way. Do it the way we just did the previous problem. Get your general answer, okay? So I go and I say, all right, well, here, it's got to be 1, so I've got to be here. So my x's have to be pi over 2 plus 2 pi k. And now, to figure out the answers between 0 and 2 pi, I'm going to start plugging in values for k. Right? That's what I'm going to do. Now, do you remember what I said would be very useful if you ever had to plug in values for k? Something that we could do before we start plugging in values for k? Like putting these together. Do you remember me showing you how you can get a common denominator between these and trying to convince you that later on this will be useful? Yeah, it's been too long, huh? So before I plug in values of k, I'm going to get a common denominator. In order to have, or add these together, so I have to get a common denominator. This 2 pi over k, or 2 pi k, is the same as 2 pi k over 1, right? And so I need a 2 on the bottom there. So I multiply the top and bottom by 2. So this should be 4 pi k over 2. Thank you. And now you can add them together. And you add the numerators, pi plus 4 pi k all over 2. Is pi plus 4 pi k 5 pi k? No. These are not like terms. You cannot add them together. This one has a k, this one doesn't. But this is the preferred form. If you're going to start plugging in k's, it's always preferred that you put these together first before you start doing it. So now let me try and plug some k's in. If k is 0, and we'll start with 0. I mean, it seems like a natural place to start, right? If k is 0, tell me what x is. It would be pi plus 4 pi times 0 over 2. 4 pi times 0 would be 0, and this is just what? Pi over 2. Now, is pi over 2 inside 0, 2 pi? Yes. So I'm going to box it. That's an answer. Now I'm going to let k be equal to 1. And plug in, and what do I get? Pi plus 4 pi times 1 over 2, which is what? How many pi's is this up here? 5 pi's? 5 pi over 2? Is that inside the interval 0, 2 pi? No? How can you tell? Yeah, it's bigger than 2 pi, but how can you tell it's bigger than 2 pi? I just want to make sure everyone understands how you can tell. What's 5 divided by 2? Well, what's 4 divided by 2? 4 divided by 2 is 2, right? So 5 divided by 2 is bigger than 2? So this is bigger than 2, so that's bigger than 2 pi. Yes? This is the way you're going to do it on all these. Just compare that. If it's bigger than 2, you're done, right? So this is bigger than 2 pi, which means I'm not going to include it, right? Chunk it. Now, do I need to keep going and do k equals 2, 3, 4? Do I? No, because as soon as I got to k equals 1, I was too big. So k being 2, it's going to take me around again. I don't want that. But what have I not considered yet? The other directions, right? The other direction, backwards. Let's just check. So I'm now going to try k equals -1. So x here would be pi plus 4 pi times -1 all over 2. How many pi's is that on top? This is pi plus 4 pi times -1. That's -4 pi. So this is pi minus 4 pi, which is -3 pi over 2. Will this work? No, because what was our restriction? We had to be bigger than 0, right? This angle is negative, right? So this is actually less than 0, right? Less than 0. You ever seen that movie, Less Than Zero? It's like an old movie. I'm aging myself up here. Robert Downey Jr., Less Than Zero? No? No? You've seen it? All right, thank you. It's kind of a weird movie. That's not going to work. All right? So we've gone the other direction. Didn't work. We're done. Okay? Again, you might be sitting there going like, okay, I kind of could see that already. Like, do I really need to go through all that? So let me again give you a slightly adapted problem, and you can see how we start to run into some issues. And that going through this is actually worth it. So here it comes. 8, 3, 4. How about this? Sine 4x equals 1. I want the answers between 0 and 2 pi. Notice also that when I wrote that, I wrote 0 to 2 pi. I put a line here between the 0 and the x, and then no line under this inequality. That means if you do get an answer that's 2 pi, you're not going to include it. But if you get the answer 0, you would include it. I'm following the convention of the book. The book is using 0 to 2 pi like that a lot. Okay, so you might be sitting here thinking, okay, well, pi over 2 again, right? It's the only angle between 0 and 2 pi. Here's the difference. The key to the problem being different is the fact that what you have in there is not just x. It's 4x. So whatever x you plug in, you're going to multiply by 4 first, right? And then take sine of it. You follow me on that? So let's just say you think the answer is pi over 2. Plug pi over 2 in here. What's pi over 2 times 4? 2 pi. What's sine of 2 pi? So 2 pi is all the way around, right? What's sine of 2 pi? 0. Is that equal to 1? No. So that answer is wrong. You see that? So that 4 is screwing everything up. So here's the way we approach it, all right? And there's several kind of methods you can do this. I want to take this kind of slow since this is the first time we're seeing it. Just imagine that that 4x instead is something different. Well, let's just call that 4xu, all right? So I'm just saying sine of u is 1, right? Then you would go around, you would do the same thing we did earlier, and you would say, okay, hey, look, that's going to happen when I'm up here, right? That's going to happen when I'm up here. So that means the angle here, right, has to be pi over 2. But what's the angle here? The angle is u, not x, right? So what I'm saying is that not x has to be equal to pi over 2, but u has to be equal to pi over 2 plus any number of rotations. You see the difference? Whatever the heck turns out to be in here, the argument, that argument at the end of the day needs to be pi over 2 plus any number of rotations of pi over 2. If that happens, then yes, the answer will be 1. Now what I'm going to do is I'm just going to switch back. What is u? For us, what's u? 4x. So this really is turning out to say 4x has to be equal to pi over 2 plus 2 pi k. Do y'all have questions on this? This is really important that you get this down. Now I'm trying to solve for x, so what do you think I'm going to do with that 4 in front? Yes. Yes. Now you could circumvent this whole step. I'm just trying to get you to see that whatever's in here, not x, right? Not x, but the whole thing has to be equal to pi over 2 plus 2 pi k. So you could just go from here straight down to here, but you need to remember it's not just x that has to be that, it's the whole argument has to be equal to that. Now, how do I get x by itself if I'm solving this equation? 4 times x, so I come through and divide by 4. So that means you divide both sides by 4. When I take pi over 2 and divide it by 4, I get what? Pi over 8. And when I take 2 pi k and divide it by 4, what do I get? Pi k over 2. Now, we're going to need general solutions, right? I'm going to need to start cycling my k's through. So I recommend you put these together first before you do that. So what would your common denominator be? 8. So I should multiply that pi k over 2 by 4 over 4 here so that I get an 8 down here, and then whatever happens up there happens up there. So what must x be equal to? Pi over 8 plus 4 pi k over 8. And then put those together. X must be pi plus 4 pi k over 8. Now I'm boxing this. This is not my final answer for the problem, but I'm boxing it because I'm at the point where I can start plugging k's in. I've solved for x, right? I've determined what x is. I've got nice fraction here. It's not 2 fractions. And I can start cycling through k's. So where should we start? Probably k equals 0 again. If k is 0, let's see how quickly we can spit out an answer. If that zeroes out, right, then you just get what? Pi over 8. Is that inside 0 to pi? Is that inside that interval? Yes. Let k be 1. If k is 1, what happens here? We get 4 pi's. We add a pi, so now we have 5 pi's. 5 pi over 8. Is that inside 0 to pi? Yes, because 5 divided by 8 is not bigger than 2. Now I go again. K equals 3. X is what? Now you're, wait, 2, sorry. I skipped 2. K is 2. Did I say 2 and write 3? I said 3 and wrote 3? Okay. So 4 pi times 2 is what? 8 pi, and then add 1 is 9 pi over 8. Is 9 pi over 8 inside 0 to pi? Yes, because 9 divided by 8 is still smaller than 2. You can see we're going to have a few more, right? Okay. K equals 3. If k is 3, you get, what, 12 pi plus a pi is 13 pi over 8. You okay with that? You happy with that? Is that, do I include that answer or chunk it? Include it, right? 13 divided by 8 is still bigger than 2. When am I going to stop? Whenever the number up here gets bigger than what? 16. I think it's about to happen, right? On k equals 4, I get 17 pi over 8, which is bigger than 2 pi, which means I throw it out. And so right now, I have 4 answers, don't I? 4 potential answers. You see the danger? I'm trying to illustrate the danger of looking at this and going, oh yeah, I know where sine's 1. It's at pi over 2. That's my answer. If you don't pay attention to the argument of the trig function, you're going to miss the fact that you actually had 4 answers, not 1. Now wait, there might be more. I never checked k is negative 1. If k is negative 1, what would you get? Well, that would be a negative 4, right, pi. And then add pi, that would be negative 3 pi. I'm already done, right? Negative 3 pi over 8. I would throw that out. Why? Because it's less than 0. Now, what if, okay, what if I had changed the problem up here? I'm not doing this right now, but what if I had said you have to be between negative 2 pi and 2 pi, like that, instead of this? Then would that negative 3 pi over 8 would it have worked? Yes. And you would have had to go k equals negative 2, k equals negative 3. And you would keep doing it until you would get a number that's bigger negative than negative 2. So you'd probably have like 8 or 9 answers. See, do you understand that? Now, I'm not doing that to you, but I'm just pointing it out. So what are these solutions to this equation on that given interval? They are here. So what I think I'm going to ask you for on the test, when I ask you to solve this equation, and the book doesn't ask you this in the homework, so just be aware of this. When I ask you to solve an equation like this, I'm going to ask you part A and part B. Part A is going to be, part A will be, give me the general solution. So give me this. And then part B will be, give me the solutions just between 0 and 2 pi or something like that. And then you give me the list. That way, you get some credit for this, but you're forced to do it. And then you get credit for that. Does that sound like a deal to you? Okay. All right, now let's start cranking it up a little bit. 835. Find general solution. B, find solutions on 0 to 2 pi. So that's exactly the way to appear on the test. By the way, my tests are handwritten. I don't type them. Like I actually write them on this tablet and then I print them. So just be prepared. You're going to see my handwriting. Some people freak out. They expect a typed out test. It'll be handwritten. So that's pretty much exactly what you would see on the test. Well, here I don't have, in the last problem was sine x equals 1, right? So I had already isolated the trig function. I had already gotten it by itself, hadn't I? Here, that cosine x in there is not isolated. So we're going to do that first. Try and get the cosine by itself. So I'm going to first you can kind of do two things here. You can move the 1 over to the other side, or you could actually add 2 cosine x to both sides. It would really be up to you, but I'm going to subtract 1 on both sides. That's what would happen if I subtract 1. And then what do you think I'm going to do? What's that? Divide by negative 2, right? Because I'm trying to get the cosine isolated. When I divide negative 1 by negative 2, I get what? 1/2, positive, right? So now I ask myself, where is the cosine function 1/2? So I go to the unit circle. Cosine is which coordinate? It's the x coordinate, right? So where's the cosine? Where is cosine 1/2? 60 degrees, so up here, right? That's at pi over 3, right? But it's also 1/2 where? 5 pi over 3. See, there's two actual places it could happen. Now, why am I not cutting off the bottom and only looking at the top? Why am I not doing that? Yes, but I thought when we were talking a second ago about the homework problems, I was cutting off. I said for cosine, you cut off the bottom too. Why am I not doing that here? I'm not even talking about the inverse cosine here, am I? Right? I haven't even brought it into play. There's no inverse cosine that I'm even talking about. You don't see the little cosine with a negative sign, right? It's not here. If it's not here, then you don't cut anything off. All right, so those are the only two places, right? How am I going to write this general solution of pi over 3? So I'm going to say here, whatever my argument was, right? My argument here is x. Whatever that argument is, has to be equal to pi over 3. But we could also go all the way around, right, and get back to pi over 3. So I need to add to this what? 2 pi k. Is that the only thing that I would make this true? No, you got to get to 5 pi over 3 also. So I could also say, or x could be equal to 5 pi over 3 plus 2 pi k. And now, let's get common denominators on both of those. So I need to multiply top and bottom here by 3, top and bottom here by 3. So we get x is equal to pi plus 6 pi k over 3, or x is equal to 5 pi plus 6 pi k over 3. Anybody have any questions on what I did there? Getting a common denominator? No questions? I was in my Cal 3 class on Monday. I went through this entire lecture. I thought it went great. At the end of class, we were all kind of talking as we were packing up. I was like, how'd it go today? Y'all understand that? All of them were like, no friggin' idea what you were talking about today. Like, they were all blown away. But the whole class, I was asking them, they weren't saying anything. I was like, okay, so is everyone okay? No questions? So this is what part A would be, right? That's the answer to part A. That's your general solution. Gives you all the solutions to that equation, all infinitely many of them. Now I just want the ones between 0 and 2 pi. So I'm going to let k be 0, then k be 1, and then when I max it out, I'll go the negative direction. This is going to go pretty quick. If k is 0, what would x be? So let's do it in this one. K is 0, you get what? Pi over 3. What about k equals 0 in the other one? 5 pi over 3. Are those both inside 0, 2 pi? Yes. Okay, if k is equal to 1, what happens? 7 pi over 3? Is 7 pi over 3 good or no? No, it's bigger than 2 pi, right? 7 divided by 3 is bigger than 2. So that doesn't work. And then the other one would be, what, plug in 1 here, so you get 11 pi over 3? Definitely no go there, right? So now I just need to check maybe the negatives, but you can hopefully you see that that doesn't work either. It'd be negative 5 pi over 3. That's negative, doesn't work. X equals negative pi over 3. That doesn't work. How you feeling? Pretty good? You like it? You like it, don't you? I knew you would. Boy, I want to kind of ease into this, but we'll go with this one. All right. Where am I? 8, 4, 8, 3, 6. Okay, I'm sorry, I didn't box them up. For B, your answers would be, well, just the answers are those two right there. Okay, that's the answer to part B. That's the answer to part A. On the test that you're taking on Monday, I will ask you this question almost exactly. So both. Yeah. I think the most valuable thing is finding the general solution. Because if you find a general solution, you can find all solutions. But then you have to know how to use the formula, like to plug in the k's and go through that part of it. How about this? Cosine squared 2 theta plus 2 cosine 2 theta equals 0. Now I'm using theta instead of x. All right, so it's x is a dummy variable, theta is a dummy variable. I could have used t in there. I could have used any letter I want, basically. I'm just using something different just to get us used to seeing different variables. So we want to know what theta makes this equation true. Anybody have any ideas? Or do you see something that we haven't seen yet so far? In the minimal number of problems I've shown you so far, we have not had what? Squared, right? But just like I said in the beginning of today's little lesson here, that when you go back and you look at your history of solving equations, right? Linear equations, you just move things around. When we got to quadratics, we tried to move everything to one side, and then we tried factoring, right? Well, let's use a similar approach here. I have cosine squared of 2 theta means that I have cosine of 2 theta times cosine of 2 theta. So there's actually two of those factors of cosine here. I have one of them here. Can I factor a cosine 2 theta out? This is what I'm getting at. If I told you I had u squared minus, plus 2u equals 0, could you factor a u out like this? U is u plus 2 equals 0. Could you do that? Yes? So what I need you to see here is that when this is written, what we really mean is cosine of 2 theta squared plus 2 times cosine of 2 theta. I need you to see that the little squared here, remember what it meant. It meant that we were taking the cosine 2 theta, the whole thing, and squaring it. So this is kind of like a u squared plus 2u, isn't it? Do y'all see that? Our u here in this case is actually the entire cosine 2 theta. There's two factors of it right there in the beginning. So I can pull one of those out like this and then leave on the inside this. Let me write it down and hopefully you'll see it. So I'm going to pull out a cosine 2 theta. What I'll be left with is what? Inside this parentheses. Cosine 2 theta again, then what? Plus 2, then equals 0. So just check, if I distribute this back through, what's cosine 2 theta times cosine 2 theta? Well, cosine 2 theta squared, which is what we have up there, right? Then if I do cosine 2 theta times 2, I'll have plus 2 cosine 2 theta. Do you all agree with that? Yeah? Okay. Now, just like we did over here, when we factor something like this and it's set equal to 0, don't we just go and set each of the factors equal to 0? Like I would go and say, all right, set u equal to 0. And then I'd set u plus 2 equal to 0, I get u is negative 2 here, and over here u is 0, and we'd have our two answers, wouldn't we? That's what we do like in college algebra. Factor, set each factor to 0. Same exact thing here. I have multiplication occurring between these two things. They multiply to be 0, so I set each of those equal to 0. So now I'm coming up with two new little equations. I have cosine 2 theta must be 0. The other equation I have is that cosine of 2 theta plus 2 must be 0. Any questions here? Now you've taken this weird looking quadratic trigonometric equation and you've reduced it down into two basic trigonometric equations. So let's look at this first one over here. Cosine 2 theta is 0. I want to know when cosine of something is 0, right? So I can go to my unit circle. Cosine is which coordinate? The x-coordinate. Where's the x-coordinate 0 on the unit circle? Here and 3 pi over 2. It's actually at both of those places, right? You okay? Come on. Look like you're zoned out there. Another dimension. Right? Cosine is 0 here and here. Now, I'm not even going to touch this one yet. I will come back, but let's not forget we have to come back, all right? But does everyone realize, like, this is its own problem now? Like, it's its own animal. We have to figure out all the answers here, and then later on come and deal with this. All right, somebody give me what I would need for this to be 0. I need the argument, right? The argument, 2 theta, has to be equal to what? So give me the general, so let's see who's going to be the most clever about this. How could I get to this one? Pi over 2, right? And then I could add a full rotation to get back to it, right? Down here, I could be at what? 3 pi over 2, and then add a full rotation to do it, right? But there was a quicker way. Do you all remember? Yeah, because look, these are directly across from each other, aren't they? So what I could do is I could start at pi over 2. Then if I add a half rotation, I'm down at 3 pi over 2. If I add another half rotation, I'm back up at pi over 2. And then I'm back down 3 pi over 2. So instead of going and looking at the two dots separately and add full rotations to get back and forth, just look at the dots as being directly across from each other and jumping from one to the next. So you can start at either one. Doesn't matter which one you choose. Let's start here at this one. That's what? Pi over 2? And add to that what? What's a half rotation? Pi k. Right? 2 pi k is a full rotation. Pi k is a half rotation. If I take pi over 2 and I add any number of half rotations, I will not only get all the pi over 2s, all the straight up and downs, I will get all the straight down. Sorry. Not all the points straight up, I will also get all the points that are straight down. That knocks them all out in one shot. But remember, that's what 2 theta was. So now I have to come through and what? Divide by 2. So I get theta equals pi over 4 plus pi k over 2. I'm dividing each of them by 2. To get my general solution, I'm going to put these two together with a common denominator. So theta will be pi plus 2 pi k all over 2. No. 4. Yeah, sure. You mean put these together first, then come through with the 2? Sure. Yeah, that would work. Either way. This is my general solution, right? That's my general solution. Questions on that? Are we done? No, we still have to go back and take into consideration this up here. So let's try and isolate the trigonometric part of this. So let's get that 2 to the other side. So we will subtract 2 on both sides. And I'm saying cosine, so which coordinate am I talking about? The x-coordinate, so I'm going, okay, uh-oh. I'm saying, where's the x-coordinate what? Negative. I'm on the unit circle, right? This is not ever going to happen. Your x-coordinate -2 means that you're out here. In other words, remember, cosine was always bounded between what two things? Any cosine function, the amplitude of this is 1, right? So I know my cosine is bounded between -1 and 1. There's no way it's ever going to be -2. So there's actually no solution for this part of the problem. Good thing for us, right? Because what if it would have been? Then what we would have had is 2 sets of general solutions. I mean, not like we should be intimidated by that, but this just goes to show you that, you know, it could happen. It could just give you no solution. It just depends. Questions? Now, did I specify in the problem an interval? Did I say solve this equation on an interval? That means you have to give me the general answer. Now, let's just for practice, let's get all the answers between 0 and 2 pi, just for practice. And I'll do it quick. So if I had said between 0 and 2 pi, theta, not x, let's see how many we would have. K is 0, what would we get? Try and go quickly through this. What do you get? Power of 4. That works. K is 1. 3 power of 4. Does that work? Yes. K is 2. 5 power over 4. That work? You can kind of see the pattern, right? It's going up by 2 pi each time. Next one should be what? 7 pi over 4. Does that work? Yes. 9 pi over 4. Does that work? No. That one got past 2 pi. Plug in some negatives. They're not going to work. So if I asked you for the answers between 0 and 2 pi, you would have 4 of them, wouldn't you? Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Yes? Only pi? No, this pi k has nothing to do with the restriction at all. It has to do with how can I get from this point to this point, back to this point, back to this point, back to this point, back to this point. I can do it by starting here and adding a half rotation. A half rotation is pi. So start here, add 1 pi, I'm here, right? Add 2 pi, I'm here. Add 3 pi, 4 pi, 5 pi, 6 pi. Totally separated from that. Yes? I think what you're asking is if you had gone to your circle and you had determined that what you were looking for were those 2 points, then you would say something like, I'm going to use x. You would say start at 0 and add how much? Pi k? Right? Pi k would be a half rotation. And then you don't even need the 0 because you just write pi k. This would be the general solution for those 2 points. Now, could you have written this? Start at pi and then add pi k? So instead, don't start at 0, but start over here and then add a half rotation. Yes, that would still work because k can be negative. So you can actually put in, if you put a -1 in here, you get 0, right? Where up there, if you put in 0, you get 0. So it will cover all the points also. It doesn't matter where you start from. It's the rotation is the key to getting to all the points. Let me give you another one. Let me start with just the idea of, can you tell me what these solutions would be? What if I told you that your solutions were at those four corners? So this is pi over 4. That's directly across, directly down, directly. So it's like the four corners type. So x equals pi over 4. So you want to start at that first one right there, right? You want to start there. And you've seen from your answer, you just told me, you've seen that you don't even have to go all the way across, right? And then come back and then go all the way across and come back. You've seen that if I just go here, that rotation is what? Pi over 2, right? 90 degrees would give me here. Then another 90 would give me here. Another 90 would give me here. Another 90 would give me here. And then another 90. And then I can start jumping around this circle with 90-degree increments and get to those 4 points over and over and over, right? So you go pi over 4 plus pi over 2k. Do y'all see that? The key, though, here is to realize that if you draw these straight across, these all hit at 90-degree angles, right? So they're all what, perpendicular to each other? So they're off by pi over 2. Be careful. Let me show you something that you could get tripped up on. What if I told you you had this situation? What if it was that angle in here was pi over 6? So I'm saying that this angle here is pi over 6 right here. And then this angle right here, the measurement is also pi over 6. And then down like there is pi over 6. And down here is pi over 6. Can you start at 1 and jump around the circle and get them all? No. Because what it takes for you to get from here to this one, right, is a certain angle. But then to get from here to the next one is not the same angle. It's different, isn't it? And then from here to here is different than the angle from here to here. So do you see you cannot jump evenly across this? So what you have to concede is that, well, these two are across from each other, right? Directly across. And then these two are directly across. So unfortunately, you will have to do this as two separate general solutions. One of them would be x is pi over 6, which would be this point, right? And then plus what? Pi k. And that would knock out both of those, right? That would knock out both of these. Pi over 6, start here and add pi k. And then you have to do these two. So what's that point right there? Or what's that angle? Pi over 6, pi over 6 plus pi k again. See, no way around that one. You have to do 2. Now, could you have done pi over 6 plus 2 pi k? 5 pi over 6 plus 2 pi k? 7 pi over 6 plus 2 pi k? And 11 pi over 6 plus 2 pi k? Yes, you could have done all 4 separately with full rotations going back to them. But now you got 4 sets of general solutions, and a lot of them are going to overlap each other, are going to produce the same points. So you want to be efficient if possible here. I hope you're understanding this. This is like good stuff. Yes. Yes. Plus pi k, and then this one, you just leave that one? That would be correct. Yep. Yes, but I would go, I'd sigh. Because we want to be efficient, right? We do want to be efficient. All right, so with that in mind, I'll try and do one more example here. We're going to do a lot more of this, okay? So I'll keep this in line with, yeah, let me try this. Haven't looked at this problem yet, so I don't know how this is going to turn out. Sine squared 3t minus cosine squared 3t equals 1 plus cosine 3t. That looks kind of messy, yeah? I'll also just make sure I'm pointing out, when you see these things, you should be noticing, hey, look, my argument's 3t, so I know that I'm going to have some weird things I'm going to have to take care of as far as the jumping around, because the 3 in there is going to throw things off. But the bigger picture is, I guess, that we have to figure out how the hell we're going to solve this. We've got sine squareds and cosine squareds and a cosine by itself. In the last problem, we had all cosines, didn't we? And so we were able to factor a cosine out. So maybe what we should do here is, since it's sine squared, maybe we should try and get everything in terms of cosine. Because we've got cosine over there, right, on the right side. We've got cosine on the left, but that sine squared just kind of throwing everything off. So I'm going to come in here and I'm going to replace sine squared 3t with something, and you're going to tell me where it comes from. What's that? I'm saying that this is equal to this. That's that Pythagorean identity, right? This is one, I told you, is probably the most important identity. Sine squared x plus cosine squared x equals 1. Remember that? And we said that you can move things around here. So if I take the cosine squared x to the other side of this equation, it reads sine squared x is 1 minus cosine squared x, right? So anywhere that I see a sine squared of something, I can replace it with 1 minus cosine squared of that something. Then everything else in the equation I just leave alone. Negative cosine squared 3t equals 1 plus cosine 3t. So what I've done here is I've made a conscious decision to try and turn the sines into cosines so that all my equation is just cosines, in the hopes that I can factor it. And I'm thinking factoring because of what? Why am I thinking factoring? Because of the squareds. So now let me collect everything onto one side of the equation, because that's the way we try and attack a quadratic. So let me put these two together. What is negative cosine squared 3t minus another cosine squared 3t? Negative 2 of them, right? So I have negative 2 cosine squared 3t. I'm also going to subtract that 1 on both sides. Oh, yeah, that's nice. They go away, don't they? I like that. And then I'm going to bring this guy over here to the other side. So when I bring this cosine 3t to the left side, it becomes a what? Negative cosine 3t. And then on the right side, I still have 0. This is just algebraic manipulation, moving everything in the equation to one side. I don't know about you, but I'm not a real big fan of having a negative term on my squared. And so what I'm going to do is just change the equation to positive. Am I allowed to do that? Can I change both those negatives to plus just because I think I'm, have that authority to be able to just do whatever I want? What did I do? I mean, there's an actual move I did here algebraically. What was it? Multiply both sides by -1. Change these two to positives, and then -1 times 0 is still 0. So that was a legal move. And it's just easier on my eyes to see pluses, to see a positive right here. And isn't this very much like the previous problem? Isn't it? I have a cosine squared 3t. The 2 in front doesn't matter. I have a cosine 3t, so I can factor out a what? Cosine 3t. Pull the cosine 3t out. What you will be left with is what? 2 cosine 3t. Be careful with that 2, right? It didn't come out. Then plus 1. You can always check your factoring by multiplying back through. Here to here should give you this. Here to here should give you that. Now that you have multiplication, you have it equal to 0, you set each factor to 0. So I have now cosine 3t must be 0. And the other equation I have is 2 cosine 3t plus 1 must be 0. We all in agreement here? Yes. Okay. Cosine 3t. This from here. Okay, so this right here, let me write it on the side. This right here is the same as 2 cosine 3t squared plus cosine 3t equals 0. And I want you to just kind of squint your eyes. This is the same as like 2u squared plus u equals 0. I know I wrote that kind of small. But this right here being squared means this, that it's actually the cosine 3t, the whole thing squared. But whatever's here, I also have another one here. So like imagine that that's like a u. This is like 2u squared plus just a u. And then you can factor a u out on that one. Here you could factor a u out and be left with 2u plus 1 equals 0. Right? If I have u squared plus u, well, 2u squared plus u, do you agree I can pull a u out? Okay. What you have to see is that the u here is actually the entire expression cosine 3t. Because it's being squared means that you can pull one out. And then over here you have cosine 3t, you pull that one out. When you pull one cosine 3t away from this, it leaves the 2, and then it leaves one of the cosine 3t's. When you pull a cosine 3t out of this one, it leaves a 1. Are you sure? Okay. Like I said before, just distribute this back through to check. If I distribute here to here, that becomes a 2, and then cosine 3t squared. Distribute here to here, and that becomes this. Let's get our solutions on this first equation. Cosine 3t is 0. I go to my unit circle now. How is it that I know I can go to my unit circle now? Because I have the trig function isolated, right? Cosine of something is equal to something. I'm at that point, so now I'm ready to go to my unit circle and look at the, what coordinate? Cosine is the x-coordinate. Where's the x-coordinate 0? The top of the circle and bottom of the circle, right? So we have 3t must be pi over 2 plus pi k, which means that not 3t, t must be pi over 6 plus pi k over 3. So I'm going a little faster through this because we've been through it a couple of times now. Since those two answers are directly across from each other, I start out at the top one, pi over 2. And yes, Danielle, you could have started at 3 pi over 2 and then add pi k. And then I divide everything by 3, and then I'm going to get a common denominator. So t is, let's see, pi plus 2 pi k over 6. The other one, I have to isolate the trig function. So I'm first going to move the 1 to the other side. Makes it a negative 1. What the hell is going on with my... Okay. Right, move the 1 over to the right side, makes a negative 1. Divide by 2. This thing's like freaking out on me. I get negative 1/2. And I've got the trig function isolated, so now I go to my unit circle. Where is cosine negative 1/2? So where's the x-coordinate negative 1/2? Two pi over 3? And where else? Oh, why is it doing that? It's weird. Let me zoom in, see if that changes it. Are those directly across from each other? No. Unfortunately, we're going to have two sets of general solutions for each of those because they're not directly across from each other. So I'm going to have my t must be 2 pi over 3, and how do I get there again? At 2 pi k. And then the other solution, that 4 pi over 3, will be t equals 4 pi over 3 plus 2 pi k. And then you go get common denominator. I'm not going to do that, but you would, right? Is this okay? Oh, wait, did I not put, I didn't put through, oh, see? Bad. It's the argument. Damn it. The argument was 3t. Then come through, I did on the other one, right? Okay, yes, I did. The 3t has to be equal to that. And then come through, divide by 3, get your common denominator, we're done. We only have 10 minutes, so I wanted to stop so we could talk about the test. Okay, so if you've looked at the review, I can already tell you we did not cover something that I had put on the review, so I just want to make sure that on page 668, I gave you some problems. Omit number 37. I just didn't get an opportunity to show you that. And that problem takes about 15-20 minutes to get going, so I don't have time. Let me see. So for the exam, all right, you may bring the formula sheet. The one I gave you, right? The one I gave you? Yes, it has a unit circle in the top right-hand corner, and it has all the formulas on it, right? You may bring that. Of course, you may have a calculator. You can have a graphing calculator. I don't have any restrictions on that. I will provide paper. I will provide the test. You don't need to bring anything to write with. I'm debating in my mind here whether or not you should have anything else. What do you feel like? And of course, you're going to want more, but I mean, cheat sheet. Well, here's the deal with cheat sheets. I mean, I'm okay with you having a single sheet of paper. You can write on the front and back of it, but you just can't work problems out. It's just, that isn't even really fair. So I don't mind you writing steps down, like, you know, go through the review problems that I've given you, and as you run into issues, you can write things down. Like maybe you need to write down the steps to graphing, you know, set the argument equal to 0. Find your test points. Remember the average. To average the points, you add them and divide by 2. But you can't just write the problems down and work them out. So as long as your cheat sheet is just formulas, steps, hints to yourself, procedures, I don't care. But if it has a single worked out problem on it, you can't use the sheet. And I will check them. I'll walk through and check them. Yes. Yeah. Like you could do, like, you know, sine inverse of sine x is equal to x as long as x is between, you know, that's all fair. Pi over 2, negative pi over 2, right? That's all good, because that's like a formula. That's a definition of something. What you couldn't do is, you know, write sine inverse of sine of 4 pi over 3 equals, and then the correct answer, and then show it all worked out how you did it. And but as you work those problems out, reviewing for the test, that's how you create your cheat sheet. You're sitting there, you're working like, damn, it would have been really nice if I would have known this. And so you write something on your cheat sheet that helps you with that. All right? Does that sound like a fair thing? Okay, so cheat sheet, I'll put here, cheat sheet. And the big thing on that, no worked problems on that. 8.5 by 11, standard sheet of paper, front and back is fine. If you want to make photocopies out of a book and you know, like paste together a bunch of stuff that has a bunch of formulas, you can do that. If you want to type it up, you can type it up. I have no real restrictions other than it's got to fit on that sheet of paper, front and back, and it can't have anything worked out. If you at any point are fearful that maybe you're putting something on that cheat sheet that maybe you shouldn't have, you should probably check with me before you put it on there. Because really, if I do walk around, I'll feel terrible. But if I walk around, I'm like, that's got a problem worked out, I'll take it away, and then you'll lose the whole sheet. But then on the other side of that is you would hate to be sitting there doing the test knowing that somebody else has worked out problems that they're following. You know, it's just not fair. So make sure you do that. Talk with me if you have any concerns. I don't know. In my email, did I say that the test won't be as long as the review was? Yeah, I mean, it won't be as long. I don't know how many questions it'll be, but I can tell you that I'm not going to surprise you with something you haven't seen. But make sure that you study these review problems, and then also study the things I do in class, because a lot of times when I make a test, I go over the review I gave you to come up with problems. But then I also go back to my lectures, and you know, I'll just kind of flip through, like, here's my lecture. I'll just kind of be like, all right, what did I do? What did I do? And I'll just go back to different days and, oh yeah, I really like that problem, you know? And so I create problems based on things I showed you. So don't be fixated on just the review. You know, open yourself up to more than just that. All right, well, nobody's asking for answers to the review. Are they in the book? I gave you all the problems are out of the chapter reviews. I believe all the chapter reviews are all the answers. Let me see. I have an instructor edition. Does anybody have the student edition? Can anyone tell me if the answers to the evens and odds are in your... It's just odds? Okay, did I assign any evens? I had a few evens, right? Yeah, there were a few evens that I gave you. But at least for the odds, you have answers, right? Well, I don't even know if I have them here. What I will do, I will try, if possible, to go through and work some of these out and post something out there. Or if you send me an email and be like, hey, it'd be really nice if I could see the answer to this one, I'll write it up and then I'll post it for everyone in the class, like put it out there underneath the files or something. All right, study. Practice studying, like study environment. Sit in a quiet room. Try and put your book and notes away and do problems. See you on Monday. Have a good day.